Hi everybody, welcome to our lesson on confidence intervals. So in this section we are moving from the probability part of the course into inferential statistics, which is what we're going to be doing pretty much the whole rest of the course. Keep in mind that the goal here is always to take information from a sample and use it to make inferences or generalizations to the population. So for confidence intervals, we are looking to construct an interval that we are some percent certain contains the actual value of the parameter, the thing from the population that we're trying to estimate, like the population mean or the population proportion or something. And the three most common values of the three most common confidence levels we're looking for are 90%, 95%, and 99%. And we write these as 1 minus alpha percent. And alpha, so this is the confidence level here. Alpha is just 1 minus the confidence level written as a decimal. So 90% would be 0.9, so 1 minus 0.9 is 0.1. For 95%, it's 0.05. And for 99%, it's 0.01. So confidence intervals are constructed as the point estimate, which is our best guess for the population quantity for the parameter, plus or minus some margin of error. So the point estimate for the population mean is going to be the sample mean. Just about every parameter, well, not just about, every parameter has a corresponding statistic in the sample. So if we wanted to do a confidence interval for the population proportion, we use the sample proportion as our point estimate. And the margin of error gives us how far off we think our estimate might be from the actual value of the parameter. I should mention here there's a thing called sampling error. And that is not a mistake. It just means that when you take a sample, the sample or the sample mean is not going to be exactly the same as the population mean. It's probably close, but it's not going to be exactly the same. So because of that, we need to know, or we might want to know, how far off we think the sample mean actually might be from the population mean. So, thinking back to what we did before with the central limit theorem, we could use that information, that formula, to generate an interval that we might be, say, 95% confident contains the population mean. So if we wanted to do that, 95%, let's look at where that comes from. So 95%, so we're looking for an interval it's two-sided, meaning we've got 95% in the middle. And so we've got 0.05 together in the tails, so it's going to be 0.025 in each tail, which means this whole area to the left of z is 0.975. So if we go over here to our z table and look up 0.975, 0.975 is right there. And that corresponds to a z of 1.96. So that's where that comes from. If we wanted to do a 99%, we'd be looking for 0.005 in the right tail, so 0.995 in the left tail. And if we were looking for 90%, this would be 0.05 in each tail, so we'd be looking for 0.95 in the middle of the table. I'll let you guys try that though. So, looking at this formula, we could rearrange this algebraically so that we solve for the population mean. Because keep in mind, that's what we're looking for. We're looking for the population mean. So I'm going to go over here because it's easier for me to write with my mouse pen over here. I couldn't do all this if my pen was writing as slow as it does over there. All right, so we've got this interval. I'm going to make that a little bit thicker in the hopes you can see it better. So negative 1.96 is less than x bar minus mu over sigma over the square root of n. If we were in class, I would just wait while you guys do it, but alas, we are not. So I want to take this whole inequality and solve it for mu. So the first thing I'm going to do is multiply left, right, and center by sigma over the square root of n. So in the middle, that cancels that out, and on the left, it's negative 1.96 times sigma over the square root of n less than x bar minus mu less than, and we're multiplying sigma over the square root of n over here as well, 1.96 times sigma over the square root of n. So now I'm going to subtract the x bar from everywhere. So if I subtract x bar in the middle, that just leaves me with negative mu. And if I subtract it on the left side, I get x bar, oh, sorry, that's negative x bar minus 1.96 times sigma over the square root of n. And on the right, it's negative x bar plus 1.96 times sigma over the square root of n. And so now I want rid of this negative. I want to get mu by itself. So if I multiply everywhere by negative 1, so negative 1 here, here, and here, I get on the left x bar plus 1.96 times sigma over the square root of n. In the middle, I get mu, and on the right, I get positive x bar minus 1.96 times sigma over the square root of n. You may remember, though, from algebra, if you multiply both sides of an inequality by negative 1, you have to switch the direction of the inequality. And so we get, instead of less than, we get greater than, greater than. So if we switch that back around, we get x bar minus 1.96 times sigma over the square root of n less than mu less than x bar plus 1.96 times sigma over the square root of n. All right, so what we end up with is an interval that can just be written as x bar plus or minus 1.96 times sigma over the square root of n. And that's what we have over here. Okay, so that's what we have over here, with one exception. I should clarify what z alpha over 2 means. Z with a subscript, I can't remember if I mentioned this before or not, but z with a subscript, and I'll put I don't know, I'll put it as A right now, is the value of Z with A as the probability to the right. So here, if we want a, we said, let's get this up a little bit. If we want a 90% confidence interval, alpha is 0.1. So this means we're looking for Z of 0.1 over 2, so 0.05. So this is the value of Z where you've got 0.05 to the right. So if you've got 0.05 to the right, it means you've got 0.95 to the left. So you'd look up 0.95 on your in the middle of your normal table. All right, and it works the same way here. This would become Z of 0.025. And that means 0.025 is to the right, so 0.975 is to the left. And over here, this would be 0.01 divided by 2, which is 0.005. So you'd be looking up 0.995 to the left there. So we've got our formula, x bar, which is our point estimate for mu, plus or minus Z, alpha over 2, so you know what that means, times sigma over the square root of n. And I put down here, notice that this assumes the population standard deviation is known. That's true. So in order to do this interval, we have to assume we know what the population standard deviation is. So let's do an example. So we've got a sample of 100 lemurs. So that's N. The mean pulse rate of these 100, so that's the sample mean, is 183 beats per minute. And we assume a population standard deviation of 20 beats per minute. And we want to find a 95% confidence interval for the mean. So our formula right up here, all we have to do is plug into it. So x bar is 183 plus or minus. We know for a 95% confidence interval, it's 1.96 times sigma over the square root of the sample size, so 100. And so that's 183 plus or minus so 1.96 times 20 over the square root of 100. That's 3.92. So 183 plus or minus 3.92. 183 minus 3.92 is 179.08. And 183 plus 3.92 is 186.92. All right, so that's our confidence interval. What does that actually mean, though? It means We are 95% confident the population mean pulse rate of all lemurs, non-hibernating lemurs, is between 179.08 and 186.92 beats per minute. So let me say just a thing or two about the interpretations. You have to be careful with them. A couple things to look out for. You can't leave off the 95% confident part of it. If you just say the population mean rate of lemurs is between these two values, you're stating something as a certainty that we don't have as a certainty. You may have heard the old movie from, it's a movie called Love Story, where they say love means never having to say you're sorry. Well, statistics means never having to say you're certain, but also never being able to say you're certain. So you have to put in there that this is not a certainty. This is only a 95% certainty. The other thing you want to look out for is point out that this is the population mean. If you were to say the sample mean, or equivalently the mean pulse rate of the 100 lemurs or something like that, that would be saying that you're creating an interval for the sample mean. But we know the sample mean for 100% certainty. It's the population mean we're trying to estimate. So you want to be sure and state that that's the population mean. All right, so that's our interval. All right, now moving on to talk about a different confidence interval. As we said, this interval that we just did is based on the assumption that sigma, the population standard deviation, is known. Well, how often do you think it happens that we don't know the population mean, which is why we're having to do a confidence interval for it, and yet we do know the population standard deviation? It really just doesn't happen. So this is why we do a different interval instead. So if sigma is unknown, then we're going to estimate sigma with S. Okay, so if we don't know the population standard deviation, we'll just plug in the sample standard deviation, which is fine, no problem, except that by estimating a second parameter, we need a wider interval because we're increasing the amount of variability. So we need a different distribution. So this distribution here in the middle, or this tall one, the blue one, is the Z distribution. That's the one we've been working with. The T distribution is the same shape, except it's wider. So the T distribution is some amount wider than the Z. How much wider? Well, it depends on something called the degrees of freedom. And I'm not going to go into the details of what the degrees of freedom is here. It's actually explained in the video that I posted earlier about why you divide the sample standard deviation by n-1. So I'll let you go back and look at that. What you need to know is that the degrees of freedom for this interval is n-1. So whatever our sample size is, you subtract 1, and that's the degrees of freedom. For For larger degrees of freedom, the t distribution gets narrower and narrower and narrower until it gets infinitely close to the z distribution. So it starts out, for low degrees of freedom, it's really, really wide. But for higher degrees of freedom, it gets closer to the z. And remember I said I would explain why we use 30 as that cutoff. And that's because when you get to about 30 degrees of freedom, the t and the z get close enough that most people say they're practically the same. So that's where that comes from. And I'll show you more about that in a minute. So this is a different distribution, which means we need a different table. Just one sec, we'll get to that. So the formula for the confidence interval for the mean, where sigma is unknown, is the same as the one where sigma is known, except for two things. Instead of sigma, we're using S, and instead of the z distribution, we're using the t. So, and by the way, we didn't have to have this before, but since we're using this distribution, we need to know either that we have a large sample size or that the data follows a normal distribution. So you would, and actually, technically it's based on the theory that, or based on the assumption that the data follows a normal distribution. But if you have a large enough sample size, you kind of waive that requirement. So what you would do is you'd really look at your data and do those things that we did last week where you were checking for normality. But that's only required if you have a small sample size. Anyway, let's talk about how to use this table and actually where this table is. So I have here a t-table. And I'll put this on our course page. So down here on the left side are the degrees of freedom. And up in the top is alpha over 2. So this is written as alpha, but it should be alpha over 2. For our purposes, it's alpha over 2. So suppose we wanted to do a 95% confidence interval with n equals 50. Well, our degrees of freedom is going to be 50 minus 1, so 49. And in the right tail, we want 1 minus 0.95, which is 0.05, divided by 2, so 0.025. So 0.025 in the right tail, and 49 degrees of freedom. So down this center column, and we're looking for the closest thing on our table we can find, which is 2.021. And by the way, if you notice here, I just wanted to point out that if you get to infinitely many degrees of freedom, you get 1.96, which is what the value was for z, for the z interval. And then the same is true for the other ones. Where you get to infinitely many degrees of freedom, you get the same as the z distribution. All right, so here, 15 minus 1 gives us 14 degrees of freedom. And in the right tail, because this is a 99% confidence interval, it's 0.01 over 2, so 0.005. So if we look for 14 degrees of freedom in the 0.005 column, 14 degrees of freedom is 2.977. Okay, and I feel like I sort of went quickly through this first one, but if the exact degrees of freedom you're looking for is not on the table, just get the closest one, the closest thing to it. All right, so in this example here, sample of 25 breakfast cereals. So that's n equals 25. Had a mean calorie count of 110 calories per serving, so X bar is 110, with a standard deviation. And by the way, how do you know that this standard deviation is S and not sigma? Well, this 17 calories per serving is described as coming from this sample of 25, so you kind of have to read the sentence a little bit. So this is S equals 17. And based on a normal probability plot, and that should be a Kolmogorov-Smirnov test, the data does not significantly depart from normality. So we know this because we've done the test. And we're going to calculate a 90% confidence interval. So if we want a 90% confidence interval, we need tail area of 1 minus 0.9, so 0.1, divided by 2, so 0.05. And we need degrees of freedom equal to, if our sample size is 25, degrees of freedom is 24. So that means our t-value, we need to look that up. .05, and we're looking for 24 degrees of freedom, so we're in this column. This is another thing I would probably print if I were you. You know, we're just going to use it probably just for the one day, but 1.711. Okay, so it's 24 degrees of freedom, and this is the 0.005 column, or the 0.05 column. So 1.711. So now it's just plug and chug. Plug in for X bar, so 110 plus or minus 1.711 times S, so 17 over the square root of 25. So we get 110 plus or minus 5.8174. So just leave that as 5.82. So 110 minus 5.82 is 104.18. It sounds like radio station. Sorry, I think I'm hilarious. And the upper level is 110 plus 5.82, 115.82. And don't forget your interpretation. So we are 90% confident. The population mean, or the mean calorie count of all breakfast cereals is between 104.18 and 115.82. All right. I do have one more example on here, but I think I'm going to give that to you to work on during class. So then that's it for this lesson. And, as always, if you have any questions or anything, please feel free to let me know.